can specify pre-existing fractures with any generic dip. So pre-existing fractures, or like if I were using those to represent faults, can have any specific strike dip orientation. Does that answer your question, Luke?
It does. So it sounds like the limitation that I knew about before is still a limitation. Good.
Okay. Yeah.
Chris, I wanted also to ask the size of the model for these cases that you're showing now with the horizontal fractures. That should be much larger than the 300 feet of the length of the stage. But even if you don't turn the horizontal fractures on, uh, I would expect if you model in the first stage, say, of the model, you would also need to include the like other regions commensurate with the stress shadow in distance away from the stage. Yet here you're limiting it to the exactly to the size of the stage. Is it because it's kind of uh, like a model of a middle stage of a middle and with a pre-stimulated mm, like other stages before this one?
Good question, Andrew. So to answer the first question, yes, if you were doing horizontal fractures, you would need to extend the model domain, right, in order to capture them. So that kind of just depends on your exact use case. As far as your second part of your question, that is something that I glossed over slightly just for time's sake. But we would use something called external fractures to account for the stress shadow from the previous stage. So in fact, if I go back to my wells and perforations panel, right beneath our well surveys were these external fractures. And if let's go ahead and actually just set one up, since you brought it up, you called me out for skipping it over. I'm going to make a new external fracture here for well MB1, and I'm going to place it 15 feet outside of the matrix region. And then I'm just going to approximate some properties for it for now. Let's just say that its total net pressure is 200 feet. Let's say it has 200 PSI. It has a half length of 500 feet, a half height of 200 feet, closure time of 4 hours, and a residual fraction of 0.15, and it is activated at 0 hours. So I'll leave this up here for people to copy down as you go. But what that is then doing, go ahead and hit refresh and turn on this external fracture. You can see that this external fracture is actually outside of the matrix itself. So it is not like a fracture that relates to the fluid flow like within the model domain. The only thing that this does is it's an approximation to superimpose the local stress change due to stress shadowing from the previous stages. So obviously it's an approximation, right? This is an elliptical fracture. It's just going to solve it on a kind of, Sneddon solution style shadow. But what we can do with that is use this external fracture to help approximate, the stress state that, a generic stage in the middle of the well might experience due to the previous stages here.
Chris, could you use this concept also in a huff and puff in a geothermal well, simulate the effects of the cooling, heating, cycling as you're doing huff and puff to show the stress shadowing that occurs in the fractures due to the cycling?
Um, yes, you could. Generally, depending upon how you're setting up the sector and like the boundary conditions, all of that would be accounted for, already internally, um, without the need for some of this. The cooling, both thermally or just, due to the kind of increasing and decreasing stress shadow. Um, the reason why we consider sector models more or less appropriate is that, within a given kind of homogeneous across the length of the well, then, any stress shadow imposed externally would be balanced back, right? And so you can almost consider the model domains to be, no displacement boundary conditions. And that is what the assumption is here. But that said, yeah, I mean, most of it should be calculated for, from the fractures themselves within the model, and you could definitely activate or deactivate things to account for any external influences that you needed to. All right. Let's see, anything else here on the mesh?
I do have
So we
have
have
another
the,
question for you, if you don't mind.
yeah, what's up,
So
Luke?
on a few times now you've mentioned activation, deactivation. I saw that there was like a start time and an end time kind of thing for the
Mhm.
perforations and that kind of thing. So what is the model doing with that? So like what happens when you deactivate, for example?
Well, it depends exactly on, what sort of property we're talking about. But
So let's say
you know,
if you deactivate a perforation,
mhm.
what does that mean? Is that supposed to simulate that you put a plug in and now you're simulating a different cluster? Um, just like
Yeah. Yeah.
I'm
Yeah.
just kind of curious what that actually does to the model. What's
Yeah. So I
preserved?
mean,
What's
in
not?
the clusters or perforations example, the reason why we might deactivate a cluster is, what if I went into the well and ran a liner and actually uh, cemented it, in place and then made new perforations, in the context of like a refrac, right? So when I'm saying deactivating a perf, it's as if it was shut off either via a plug or some other mechanism. Um, with regards to like other applications, you know, wellbore plugs is something that we can specifically model, right? So say you went and set a plug, you could have activation, deactivation times for that. Um, there's various things just operationally, if I'm, changing something about the well that I may need to include for that.
Okay, so I guess maybe if I reframe that. So if you were to deactivate something like a boundary condition or a fracture or something like that, is there times that it would do something squirrely that we should be aware of?
Uh,
Like it deletes a
uh,
bunch of elements or something?
Nothing that comes in mind. Um, um, I guess the only thing that pops in mind related to that question is if you set the permeability of a matrix element to be 0, then the model considers that layer, that matrix, to be deactivated, meaning that it won't count the in-place volumes. So it's not exactly probably what you were getting at, but that's the biggest one that comes into mind. Other than that, it's meant to be kind of extensible or flexible, right? The whole point of the ability to activate or deactivate something is so that, you know, you can have everything within a single timeline, right? And I'm not needing to make an edit to a simulation and running from a restart or something like that to test out a particular use case. Um, you know, for example, let's take refract again. I'm able to activate new perforations when I go and recomplete the well. And when I deactivate kind of the existing perforations, it doesn't really affect the early time, flow for those. But I'm just kind of turning them off like they've been sealed. So yeah. But nothing like that really comes into mind that would be big red flags to be
Okay.
aware of.
So if you create like a new parent-child type stuff, you create some fractures, and then you deactivate the perforation that created that fracture is still going to be there going forward in time with that model, that simulation, right?
That's correct. That's correct.
And it'll
The
still be
the
creating the stress shadow that it had.
absolutely.
Can it still drain?
It
Like
can still drain if it's connected to, say, like a different well or perhaps a different perforation
what about flow behind casing?
or with flow behind casing.
Is flow behind
So
casing in the model?
correct, it is.
Okay, so even if you disable perforation, you can still have flow behind casing.
So let's say that I had this well here and this was a apparent fracture and I had turned off this perforation. But this fracture already existed and there was flow behind casing. Depending upon the settings, right? You would need to have a connection there. But if it was set up such that there was flow behind casing, this cluster could still communicate into this fracture. Correct.
Yeah, that's the principle of what happens. And then that's in the model.
Yep. And I'll talk a lot about some of the various kind of collision and connection parameters probably tomorrow and Wednesday.
That'll be really useful, Chris, because that's what's happening in geothermal EGS systems, I think.
I definitely agree. I mean, I think even in unconventionals too, for shales and how much isolation we actually have around the wellbore is sometimes questionable. So I think that some of those kind of auxiliary connections, near wellbore, longitudinal fracture potential, stuff like that, is really important and kind of fully accounted for in the model, though it does take some calibration at times.
Chris, maybe you'll cover it tomorrow, but maybe it's worth just a quick note that fractures in the model don't necessarily initiate directly where the clusters are, and that's a controllable parameter to some extent as well.
Very true. Yeah, we'll take a look at that when we examine the results from this initial simulation. Alrighty, I'm gonna keep chugging along here. Looks like we've got about 30 minutes left, so we'll just see how far that we can get. So I'm gonna jump over to the fluid model options. The fluid model panel is where we basically define everything about the hydrocarbons in place. In the geothermal aspect, this is a little bit less important, but for anything in unconventionals and for oil and gas, it is. So by default, we were using a black oil model. So here on the fluid options panel, I'm specifying that my hydrocarbon phase is all oil and some properties relating to the hydrocarbons. So what the initial bubble point dew pressure is, some properties related to the water viscosity, water compressibility, densities of stock tank oil, stock tank gas, stock tank water, and then my actual black oil table. So you can see as a function of pressure, I've got my oil formation volume factor, solution gas oil ratio, gas formation volume factor, and oil and gas viscosities. Now, commonly, you may have data like from Whitson or pt5 or another software that could, import or generate your black oil table for you. If you wanted to use that, you could just go to the black oil library and say import, in an Eclipse format or a Whitson format, and import your black oil table directly. For our purposes, we don't have that. The only data that was given to us or that we had available was some very basic information from the fluid test that said that our reservoir temp was 170 degrees Fahrenheit. Our initial GOR was 1500. We had a oil API gravity of 32, and the saturation pressure was 2400. So for us, we're just going to use the black oil wizard, which is going to just approximate this fluid model, given this information. So I'm going to just add in that information there, and you can see the relevant papers and correlations that we are using. I'm going to say reservoir temperature of 170, initial producing GOR of 1500. Our API gravity is 32, and our saturation pressure was 2400. I'm going to go ahead and hit apply. And you'll see that it will have updated the bubble point and then generated a brand new black oil table based upon those correlations. As with before, like in the static model table, I've got these three little bars here that I can actually click to plot and visualize what my fluid model looks like. So I can look at formation volume factors and solution gas oil ratios as a function of pressure. If this was a compositional simulation, this would look a little bit different. So no need to follow this, but just to demonstrate, if this were compositional, you would have a table of your components, and I would need to specify, my molar mass, critical temperature, critical pressure, eccentric factor, and volume correction factor for each one of my components, and then I would specify my flash composition and then any binary interaction coefficients that I had from my fluid model. In this case, we don't need to deal with that because we're just going to use the black oil model. What I will say for geothermal folks, you'll tend to use a compositional thermal model, but with no components. So you'll just leave this blank. But then that allows you to specify, water density properties as a function of pressure, temperature, and salinity. So that is kind of important for the geothermal application. But we're not going to do that. I'm going to go back and change this to black oil. And that's the case here. You do also have the option to use a modified black oil model. So to include your RV, the volatilized oil gas ratio. If you were modeling a highly volatile light oil or retrograde condensate, and then I also have the ability to have, multiple different fluid regions. If I had multiple different fluid models, I can highlight that later this week if need be. Any questions just on the fluid model page? I know that was quick, but the fluid model is kind of a fluid model, so pretty simple. Typically, you would have, this from some other software, unless you were just using our generic correlations.
So there is one thing I'm curious about as you're going along here. When you're done going through this process, does it create like an editable text file or something like that for the actual input deck for the simulation? Or is there
Yeah, good question.
like just save all this stuff and you can share that file or something?
Yeah, let me go ahead and save changes, and I'll clarify that. I'm going to save and exit real quick, and I'm going to jump back to the builder just to show. So this Bakken tutorial, the one that we've been working at, I'm going to say click on the simulation, and I'm going to say open simulation folder in File Explorer. So I'm just going to pull up basically the associated files for this simulation. So if we look at I know my text is a little bit small. I don't know that there's anything I can do there, but if we look at just in the File Explorer, this is the hierarchy down to where this simulation is. There's several files here, but the two important ones are this input file and the settings file. The input and settings file, these are the two files that define everything that we were just looking at in the simulation. And in fact, if I were to open this up, these are meant to be human readable. So behind the scenes of the UI, you technically don't have to use the UI at all. You could just manually edit this file if need be. And it's pretty simple. It's meant to be human readable and have descriptions of the parameters, but the basic structure is just, variable name, value. So the short answer is yes. Yeah, ultimately this is just a text file. When we go to run a simulation, which we'll probably hit tomorrow morning, all it's really sending to the cloud is this settings file and the input file, each of which are these text files. So they obviously do get a little bit long.
And I assume that there's if you need to access special features, you'll have to use that settings file or anything that's not in the UI yet.
Yes, as of this moment, we just had a big release, so I believe that everything is included in the UI. That said, if you're working with Mark or some of our developers, and let's say we added a new feature to the simulator that isn't yet in this version of the UI, you can either manually edit it in the text file, or under the advanced options panel, there's this additional manual settings. This is how you could just enter keywords and other settings that aren't yet in the UI itself, and then they'll be included.
Makes sense. Thanks.
All right, so I think that was everything about the fluid model that was important. There's one thing I did want to mention, because it is helpful on the hydrocarbon side of things. That's something called black oil tracers. What this allows you to do is set up, uh, basically tag your fluid in place, either if you were doing a compositional model or a black oil model, with a traced component, and that allows you to really clearly and quantitatively match geochem. So if I had TLG, time-lapse geochemistry data that I wanted to model, I can say that certain layers have 0.001 mass fraction of this black oil tracer, and it will model this tracer component in the same way with the same mass balance that it would kind of the core fluid model itself. So you can do this with the hydrocarbon components, and you can also do it with the water solutes, which we'll touch on here shortly. to track, different quantitatively track, relative production from different layers, or, injected versus produced, or reservoir water, so on and so forth. So lots of ways to understand what fluid is coming into your well and where it's coming from. All right, next up is the fracture options panel. If we look at this panel, this is basically all of the tuning parameters relevant to fracture propagation, as well as fractures in general. So this is a very big panel. All of these parameters here up top are kind of the most important tuning parameters for fractures. And so we have them up here pulled up to the very top, but if you can see when I open up the kind of advanced options panel portion, there's a lot more down here. We're not going to really adjust anything here for now, but we will definitely hit on it as we get into history matching. But the first key thing to look at is just everything up here at the top relating to fracture propagation, water banking, and then the fracture connections, which I just recently mentioned, but we'll dig into in more detail.
Chris, a lot of these variables are, when you're doing a field study, you only know maybe at best a range of possible values for some of those parameters for determining the fracture properties.
Mm-hmm.
Does ResFrac have a ability to do, I guess instead of auto history matching, because there you're trying to match against actual performance, a probabilistic approach where on variables that you don't have great certainty on their numbers, you can put it in a range and it'll show you results, like a range of possibilities of potential results?
Yes, we do. So one type of the sensitivity analysis module that we have is what we call uncertainty quantification. And this would be your kind of standard Monte Carlo style analysis. So say, for example, you had a model realization that you liked, but you knew there was, say, uncertainty on perm and porosity and water saturation. You could provide like your mean value plus a standard deviation, and say that, okay, here's what my water saturation should be, but I'm going to give it some, uncertainty normal distribution. And then it can stochastically, spin up 30 Monte Carlo points, right, to sample that uncertainty, and then, you could compare the outputs. So that would be one method, right? If I've, would be to say history match to what you think is a reasonable realization, and then run an uncertainty analysis on that to see how some of the uncertainty values would affect your output. And maybe some would be more important than others, and some might not have, might have a relatively low effect in comparison, and then you can hone in on those uncertainties.
Great. Thanks for sharing. That's very
Mhm.
powerful.
Absolutely. There are definitely some companies out there that take uncertainty as part of their workflow pretty seriously and propagate everything through a P10, P50, P90 headspace.
Right. Exactly. Yep. Thanks.
Yep. All right, we'll dig into more of this panel later. But in the last 10 minutes, I still want to see if we can hit propants and water solutes, and then we'll handle the rest when we start up tomorrow. So here on the propants panel is where we define basically the details about our consumables, for our stimulation. So we have a propants table and a propants mixture table. In the propants table, we define a name of a given propant type, its diameter and mesh size, its density, and then some parameters relating to the propant pack conductivity or permeability. So for our purposes today, if I look at my fluid and propants table, or stimulation design, we are running mostly 100 mesh, slick water design. So I might want to go ahead and create my 100 mesh, and there'd be a lot of ways to do this. But for now, I'm just going to duplicate this row, and I'm going to call it 100 mesh. I'm going to say that the diameter of that mesh is 100. And then I'm also going to say that I have a new mixture that I might just call my 100 mesh propant. And I'm going to say that 100 mesh is 100% my 100 mesh component here. Now, this might seem a little redundant, like why do we have a propant and then a propant mixture? But the reason is due to two different kind of methodologies for specifying what your propant is. This one methodology is just that we are going to define a singular component with a singular mesh size. In reality, of course, we're never pumping a single mesh size. We're pumping a 4070 that has some range of distribution, or more likely nowadays, I'm seeing people pumping, 4140 local sands, right? That have a pretty wide distribution of components, that they might measure from a sieve distribution. So you have the ability to, pump a mixture that's representative of full distribution rather than a singular component. What might that look like? So don't follow along here for this portion, but I'm just going to give you an example so you can see it. If I go to my propant library here, I'm going to go to import, append, and we've got some built-in examples here. If you want to just use some default here. But I'm just going to go find an example of one of the mixtures that we have. Let's just say this generic 4070 mixture. Hit apply. And you'll see that will kind of include that. So you can see in this generic 4070 mixture, I'm actually specifying a 100 mesh component, a 70 mesh, a 55, and a 40. And then in that propant mixture, I'm defining my relative mass fractions of each diameter, right? So two different ways, I could just mesh, represent this 4070 as just a, unimodal single component with a 55 mesh diameter, or I could represent it as a more generic mixture. No not a lot of pros or cons with, either case. Both are helpful. For really, really big models, right? This is, more components that it's trying to track the mass fraction of and model in the simulation. So that would be one reason not to, is purely for a runtime concern. But either way works depending upon your use case. I'm going to go ahead and remove these since that was just for demo. And I'll finish setting up my 100 mesh. Now, in our case, in the data that was provided, we actually had prop tester data. So I can see here that I was been provided, conductivity data for this propant. And I might want to go ahead and kind of include this data as part of my 100 mesh. I want to tune my propant conductivity to match these values. We can go ahead and do that with the propant conductivity wizard. So once I've set up my component and my propant mixture, I'm going to go to my propant conductivity wizard. I'm going to say that I want to look at my 100 mesh propent, and I'm going to paste in that data. Of conductivity versus effective normal stress. Now, we have the option here to provide a conductivity multiplier. This is just a shortcut if we want to scale down from API spec. What we have often found through many years of work now is that API spec seems to be a bit optimistic compared to what we would assume at field scale values. It could be a scale effect, it could be just that API spec methodology just doesn't account for other factors. But a good rule of thumb is to reduce, API spec conductivity values by 10 to 20 times smaller to represent the conductivities at field scale. So we will go ahead and add in a multiplier here of 0.05 to represent kind of a 20 times reduction in this provided conductivity. I'm going to go ahead and hit apply, and you can see what it did there is actually tune this K naught value and the propant pack gamma in order to match the data that we specified. So what are K naught, F, and gamma? Well, these are the parameters that control, the propant pack permeability. So the way that we determine what the permeability of our propant pack is from the modified Kozeny-Kármán equation, of which this K naught value is a multiplier. And then I've got, for the relationship between propant permeability and effective normal stress, this is the propant gamma. So K naught will linearly raise or lower, the y-intercept of this chart, whereas gamma will make the relationship between conductivity and effective normal stress either shallower or steeper.
Hey, Chris, looks like we got a question from Luke.
Oh, yes, Luke.
Yeah, and I know I'm kind of causing you to go over time here. So on the propant hysteresis, how do you handle cyclic loading?
Good question. So there are settings to basically either allow propant conductivity to be irreversible or partially irreversible. So if I scroll down, I have to remember exactly where it is. Oh, here we are. So here's one of them. So right now, propant bed conductivity loss is reversible. I could turn it to be fully irreversible, which means that once, basically, each individual fracture element with its propant concentration will remember, the highest effective normal stress it got, and it will never recover that. But that is fully irreversible. Alternatively, you can do something in between, and I believe that is irreversible propant pack conductivity table versus effective normal stress. So what I can say is that only a portion of that propant conductivity is irreversible, and the rest follows some hysteresis. So for example, if I had propant permeability and effective normal stress, and this was my kind of original curve, let's say that I, put some values here in this table, I could actually have it follow a line that looks more like this, where it comes down, reaches some value, and then maybe only goes up like this. So you could have some level of hysteresis by playing with these two values.
Okay. And then another question that I have in mind, as we get closer to running our own simulations, is just tricks for keeping the computational burden down, because things like this tend to drive computational burden up a lot, plasticity and things. It'd be nice to just make sure that and don't end up checking a box or something that massively increases the compute time without a commensurate benefit.
Yeah, what I would say is that most settings like this don't particularly have a big influence on compute time. Um, the main thing I think, if when that's a concern, is just setting up initial model scope appropriately. So how big of a model we're looking at, what is the size of your fracture elements? There can be other considerations, at the margin. But the only reason why, like, say adding a feature such as this, or another more detailed feature would ever cause a simulation to be slower is if it caused it to be poorly conditioned for the numerical solve, which theoretically shouldn't happen. And if it does, then that's a bug we should fix, right? Other than that, the main driver is just going to be model scale. So that's probably the top line consideration. Everything else will be secondary. All right, that is our time for today, and I will honor